Good morning and welcome. Now we want to start to look at hyperbolic problems. And you saw already with radar on Tuesday examples of that for the wave equation and for the linear advection equation. And we shall concentrate on the linear advection equation. So that's chapter 7. First, we want to look at the physical and mathematical classification of these equations. And we start with the one-dimensional linear advection equation. That is sometimes also called a convection equation or 1D linear convection equation, or in the book it is also called first order 1D wave equation. So called first order, you find also in some books also called one way. Wave equation. So I prefer the linear advection equation in order not to confuse with the wave equation. And that is the following. We have the time derivative of the transport of a quantity that is transported, which we call u, plus an advection velocity c times du dx is equal to 0. And we assume that c is constant. And we have that with an initial condition. Later on, as usual, I'll abbreviate that with IC. So we assume that we have a solution given at the time t equals 0. And that it can be noted by u0 of x. So that is our initial condition. And that describes the transport or propagation of a flow variable that can be essentially anything. But examples that we shall consider are temperature. I think that is the example that we shall consider in the exercise, the next exercise, exercise 6. But it could also be concentration. Concentration in a liquid or gas or whatever. It could be velocity, it could be pressure, and so on. we have that in a one-dimensional isotropic medium. And if that is transported or propagated with a constant advection velocity, c, and that can be positive or negative. So it is so that is what this describes, and so it is just a simple transport. We have some given initial condition, and that is then just moved with a constant velocity, and either to the right when it's positive, or to the left it's negative. We'll see examples in a minute. The interesting thing with that is we have an exact solution, which is quite simple. And we'll use that when we test the numerical methods. The exact solution is 3, that the solution at any time x, any point x in space, any time instant t, is equal to the initial condition u0 taken at x minus ct. So we go back in space from, or if c is positive, then we go back in space by this distance. That is the distance that, say, the flow travels in the time t. That's, so c times t is the distance. And at that point we take then the initial condition. You can prove that by simply inserting it into the PDE and also checking that the initial condition is satisfied. We'll discuss the boundary conditions in a minute. So for this equation it would essentially not be necessary to solve it numerically because we know the exact solution, but we cannot use it if c would be variable, it would be more difficult, and if we would have a nonlinear problem. So this serves as a test problem for more complex problems. So then we can look a little bit at this exact solution first. What we can realize is that if x minus ct is constant, that can be on certain lines, then the solution is constant, because then we always go back, or we always have the same value here. If that is the same value, the solution is constant. So there are certain curves on which the solution is constant. These play an important role. Constant on curves, following ones, that is when x minus ct is constant. And that's equivalent to saying that x is equal to ct plus some constant that we call x0. So if x0 is this constant, that is something. And these curves have then the slope c. They have the slope of the advection velocity. So these curves characterize them by their slope, note if we do this, x is no longer an independent variable. It is dependent on t. So then we can compute the slope. We can see immediately this is c. And these are called characteristics. They play an essential role in hyperbolic problems. We see here why. On them, in our case, the solution is even constant. So we can now look a little bit more on these characteristics. Assume we have a solution u that is satisfying our linear advection equation, we can simplify the linear advection equation. So on characteristics, the PDE, in our case the linear advection equation, can be simplified to the following ODE. And that is, when we are on the characteristics, then, as we just noted, x is no longer independent, it is a dependent variable, it depends on t. So then we can take the classical derivative of this with respect to t, and we find out that this is 0. And that means that the velocity, if this would be velocity u, or the quantity that is advected, that is constant on characteristics, what we have already seen from the exact solution. So first let us see why we can do this. So we do proof here. We have this d u of x of t, t dt. And we suppose that u is a solution of the linear advection equation. So now we look at this particular derivative, and then we simply use the chain rule. So we derive u now partial derivative with respect to t. And then we derive it with respect to x, but x is now dependent on t, so we have then to add the dx dt. And if we are on a characteristic, then the dx dt is equal to c. So this here is then, if we are on a characteristic, then this is equal to c. And then we have the PDE. So then we have here du dt plus, now we write the c in front, du dx, and we have assumed that u is a solution of that equation, so that is 0. So then this is true, and then we have an ODE. We have reduced the PDE to this ODE. That means u is constant on characteristics. We could also have a more complex problem if we had a source term. Then the source term would remain. That's not a problem. It stays still in ODE, and on the left-hand side we would have this derivative. So from 5 we can see that u of xt, that is then constant on characteristic. Constant So then we can look what that means. So let's see. Space. So let's assume we have our domain X, and we write time in this direction. So this is now something we shall learn, that we look at the xt diagram. And below we want to look also at another way. We want also to look at the same domain X, but here we want to look in the u direction. So what a u, our solution. So first we shall assume that we have the initial condition, which is the u0 of X. So, and let's assume we have something, say a half sine, some discontinuity, something like that. So that is supposed to our u0. And our characteristics will be curves that have the slope c. And they can be represented in this way then. So that means we have them here. They are all parallel. And so these are the characteristics, and the slope dx of t is equal to our Vection velocity c. So now this is time 0 here. And now that if we want to go to some time, let's see, want to go to some time here, say call this t1 for example, then we know the solution that originally was at, say this was also in x0, that will be constant on this line. That is what we derived. The solution is constant on characteristics. So when we are then at the time t, the solution will be the same as there. So that means we have then the distance traveled in that time. This distance here is then c times t1. We look at that. Here we have this distance here between the times, that is our t1. And then we can see that the slope, which is dx over dt, is c. So that means this our initial condition has traveled this distance ct1. That means if we look now down here, what was originally here, that has now traveled to this point here. And we can do that for every point of the solution. For example, if we look for here, in the initial condition, initially we were here, but we have traveled here ct1. So that means when we have traveled this distance, that will be then at this point here. So that will be then at this point here. And also every point, also this point here, that will have traveled a distance ct1. So let's see, this was ct1, this is ct1, and also this point will have traveled a distance ct1. So then we can try to plot then this solution after time t1. So the whole profile is just translated by the distance ct1. So let's try to see what that is. So then we will have, let's see, go down. So we will have then something like that. Oops. That will be here. So So this is the solution then u of x t1. So the solution is just, maybe I indicated in the red here, is just transported a distance ct1. Form is just the same. It is just moved. Then we can everything identify, both as we saw here in the plane of the solution and also in the xt diagram. And this is, viewing this is quite useful. We shall use that in a minute for looking at the boundary conditions. Let's look at this. So here is first the initial condition, and it is plotted in such a way that we have x here. And this is now, t will be plotted here. Now we don't see it yet, but this is the solution at t equals 0. And the solution will be plotted at every time instant. So it will see then many solutions, each for each time instant. And then we have u in this direction. So then we let it, oops, yeah, here we are. So we see then the solution, how it develops in time. It is a sine, and it is just transported. The shape is completely unchanged. It is just transported. So here now we see x, here is t, and there is the solution. And now we see also lines below, and these lines are actually the characteristic lines. We'll see that in a minute, what that means if we view that from another perspective. Let's see if I can get that. Yeah, roughly like that. So what we can see here is that the crests, where the solution is highest, for example here, they followed exactly this line, dx dt equal c. And also the troughs, where the solution is lowest, also follow the troughs. Every solution is constant on these lines. So, and that are the characteristic lines. So therefore they play a really very important role. And as you see, the solution is completely unchanged. It's just transported. Let's try to look from above, and then we see then the xt diagram that we have. So now we see here the x, and here we see the time t. And if we have any solution here, then we know it is constant then on the characteristics. So we know then the solution further on in time. But we can also look backwards. For example, if we are at any point in the domain, for example here, some xt, we go back, and here we hit the boundary. So if we would have here a boundary value problem, we would have to give a boundary condition here to tell the solution what is getting in. So this will be then an inflow boundary. If we have a propagation to the right, then the flow variable will travel into the domain at this point. So there we have to give a boundary condition. But if you look at the right boundary here, there we can trace back the solution either to the initial condition, or if we are far out here, we have just, I think, an example. It's further out, if we would get down here, we would get to the left boundary. So that means we must not give boundary conditions at the right boundary where the characteristics are leaving the domain, because there we can trace back the solution either to the initial condition or to the left boundary, where we have to give boundary conditions. So this is extremely important in computational fluid dynamics, to know where you must give boundary conditions and where not. And that you can understand already from the simple linear advection equation. So let us note that regarding boundary conditions. First, I would like to make a remark to this. What we already said, the shape of the solution u of xt is the same as for the initial condition u of x0, which was our initial condition u0 of x. But it is just transported a distance. Transported a distance. So if we look at time t, it is transported a distance c times t. In our example, this was t1, certain time instant. So now we want to make this remark on the boundary conditions. So we have the situation that we have a domain. We could have a similar situation as there, but we take it here. Because now we want to mark here a left boundary xa and the right boundary xb. We shall write here the time. So we are then in the same situation as in this example of the animation in the xt diagram. And we assume again that we have characteristics where c, the advection velocity, is positive. So it means we have characteristics that are so these are the characteristics. And they have then a slope dx of t dt is equal to c. And we assume here that is important that c is positive, because that decides in which direction we are moving. Here we are moving to the right. So in this situation we argued that we have to give boundary conditions at the inflow, and the inflow is the left boundary. So here we have the inflow, and here boundary conditions are needed. So we have to prescribe boundary conditions at the inflow. That means, let's see, we are now at number 6. We have to give boundary condition, and that will be, we have to prescribe the velocity or our flow variable, velocity or whatever, at xat, that has to be given as a function of t. That is for c greater than 0. So then we have to give the boundary condition at the left. And you will study the situation when c is negative. then it is just the opposite what we discuss now. The other thing is, when we are at the right boundary, then, as we argued, if we are at some point here, we can go back on the characteristics and either hit the initial condition, t equals 0, so t equals 0 here, or if we are far out and we go back, we will hit the left boundary, where we have the boundary condition. So then the solution is determined at the right boundary condition, at the right boundary, and we must not give boundary conditions there. So at the right boundary, no boundary condition must be given. So here, the right boundary, no boundary condition. So, and we can then also distinguish where the solution is determined by the initial condition and by the left boundary condition. And actually the distinguishing line is from x0 in space and 0 in time. So it is this characteristic here. Anything that is on the left is determined by the left boundary condition, and anything to the right is determined by the initial condition. So, solution determined by, here it is boundary condition, and here this part is the initial condition. Any point here in this part you can trace back to the initial condition, and here you hit the left boundary. So, and as I said in the exercise, you will think the other way round. You will look at a situation when C is negative. So then it is just the opposite. Then characteristic will go this way, and boundary conditions must be given here, but not there. Okay, so then this is a point that you will face in every flow simulation. When you are asked to give boundary conditions, then if you have an inflow boundary, then you have to give the quantities needed. And at outflow, if it's quantities transported, you don't need to give boundary conditions. So the boundary conditions that we discussed here are, and we call Dirichlet boundary conditions. So this is a Dirichlet boundary condition. Dirichlet boundary condition, and that is given at Dirichlet boundary condition that is given at an inflow boundary. There we give the value of the solution itself. We can have also another type of boundary condition, that is when we have periodic boundary conditions. And that was the example that we had here. Periodic boundary conditions. Periodic boundary conditions, then we have that u of xat is equal to u of xbt. So the solution on this side, this boundary are the same. And that was the example here with the sign where we had this. So that is then if we have a periodic problem, where we have a period in space, which is then L equal to xb minus xa. So that means that it is also true for the whole x that we have this period, that we have u of xt is equal to u of x plus lt. So we can simply add, in this case, the period was 1, for the sine or cosine, but it can be anything. So it simply means that when something is leaving the domain, in that case on the right, it is entering on the left. So let's see if we could see that here. It's hard to see. Give an example of a periodic problem. If we have a sine or cosine, then that is easy, but it can be more complex than that. So let's see, we would have xa here, we would have xb here, we would have u here. Then if we have something outside, let's see, that we are not taking into account for the moment. Get this here, would be roughly like that, and then we would continue here, and so on. So then everything would repeat itself. So the value here and the value here, they are the same. But also if we go outside, if we are at any point here, we find it again here. Or if we here outside, anything we are here, that we will find here. So that would be an example of a periodic problem. And that we have in a couple of situations, not the least in turbomachinery. We have in the circumferential direction, we have naturally periodic boundary conditions. Okay, so then we now know something about the linear Vection equation. Let us look also at the wave equation. So then let's look now at the second order 1D wave equation. Usually just says the 1D wave equation. It would be 9. At the second derivative of our dependent variable u with respect to time is equal, and here we call the propagation speed c, and we have c squared times the second derivative of u with respect to x. And in this case, c is also constant, but here it is always positive. And here we need not just an initial condition for u, our propagating quantity, but we need also initial condition for the time derivative of u. So this, of course, we have now here second the time derivative. Turns out that we need then at x initial condition for t equals 0, called f of x, and an initial condition for the first time derivative of u with respect to t, which we call g of x. And that describes the propagation of waves. Propagation of, and that can be acoustic, that is what, for example, I have been looking at. Elastic, that is important for seismic problems, and electromagnetic. Waves. And if we are looking at the 1D, we again assume that that propagation is in a 1D isotropic medium. And C, as I already said, is should constantly positive, is the wave speed. So to also have the light, it would be the speed of light. And for acoustic problems, C will be the speed of sound. Do you know the exact solution? Have you seen that in math? D'Alembert's solution. Okay, then you will see it now. That is given, for example, in our textbook. Fletcher, Kendall, Anderson. So there's exact solution. 9 with the boundary with the initial conditions 10. And that is then 11. U of xt is equal to 1/2. And then we have the initial condition for U. For example, if we have acoustic problems, say the acoustic pressure, for example, U would be the acoustic pressure, and that would be the initial condition for the acoustic pressure at x plus ct plus f of x minus ct. That reminds us what we had for the linear advection equation. So in a way, this is modeling both the linear advection to the right and the linear advection to the left. So it's having that, and it's then having also another part, which is 1 over 2c, or wave speed c, times the integral from x minus ct to x plus ct, where we integrate over the first time derivative for t equals 0. So that is our D'Alembert's solution. And you can show that again by just putting it into the PDE and doing the derivation and see that that is satisfied, and also that the initial conditions are satisfied. So, according to our classification in the beginning of the course, this, we can identify that, fits into our pattern. We had x and y, but here we have t and x, similar. That is a hyperbolic second order equation. So that is the characterization that we have there. So the PDE, we know that. PDE, that is our wave equation, is hyperbolic. That you can do by using the classification that we had done in section 2.3. Just to identify t as x and x as y in that case. And then we get characteristics from that, which are given by plus and minus the wave speed. So, we have characteristics, so it means our equation 9, that's characteristics. plus and minus c. What do they look like? Now x, we have t. Then we have patterns that go in both directions. So we have, say, with c. So these are then the characteristics. And then we have one class that is going to the right, another class is going to the left. Let's take a different color. And so on. The ones going to the left, give them, label them number 1, and they would have the slope minus c. And the ones going to the right, the white one here, give them number 2, they would have the slope plus c. So, and then you can imagine when we have now boundaries, we would have to give boundary conditions on both sides. Because if this would be a boundary, for example. Would be a domain here, would be our domain. Then we have to give boundary conditions for the waves entering here and here for the other class, entering from the right. That is, we have to give them boundary conditions on both sides. So here it is a little bit more complex with the exact solution. You see it from here. If we have g equals 0, we have just a superposition of the initial condition going from the waves going. These are going to the right, and these are going to the left. And if we have g, then we have also to take that into account. So that gives us then an idea what we are talking about here, hyperbolic problems. And the thing that I forgot to say was that the linear advection equation that we had in the beginning does not fit into the pattern of the second order equation. It is a first order equation. But the linear advection equation is of a type that, so here we can say the linear advection equation, so that was a thing that I forgot to say. The advection equation is also hyperbolic. And when we say that, we argue that it can be reduced to an ODE on characteristics. So in this sense, we can identify it also as a hyperbolic system. There is more theory to that, but we should not go into detail on that. That will be part of follow-up course, TP 4165, computational heat and fluid flow. Because you can write this equation in the form, we have a du dx equal to 0, or say a 0th or constant term, then what we need is that A is a coefficient matrix that must have real eigenvalues. So if A has real eigenvalues and linearly independent eigenvectors, so the system, first order system, for that we have not yet had a classification. is called hyperbolic. So then it can essentially be reduced to a constant matrix to linear independent ODEs that we can solve very easily. In our case, the situation is much easier because we have just a scalar problem, and A in our case is just a constant C. So that is definitely real, and eigenvectors, we take one, we have just need one, so that is a trivial thing. So, but we can go here more complex. We can have more complex linear systems. But this is useful to characterize first order systems. Okay, so then we have now an idea of the background, what we are talking about advection for linear advection equation and propagation of waves for the wave equation. And both are examples of hyperbolic problems. So then we take a break of 15 minutes now.